Good afternoon, everyone. I'd just like to introduce myself. I'm Craig Harris. I'm lead technical sales for Velocys, an advanced Fischer-Tropsch licensing provider. Today, I'm going to talk about a topic which is at the intersection of the climate, innovation, and aviation growth. I'm going to touch a little bit on the current SAF opportunity in India, look at various pathways, and then look how Velocys is uniquely positioned to help India meet its goals of building a scalable, sustainable aviation sector. So, as mentioned by the previous speaker, India has aligned itself with some realistic goals to produce 1% of SAF for international flights by 2027, increasing to 5% by 2030. All of this is aligned with the overall framework in India to achieve self-reliance in 2047 and net zero by 2070. Currently, the market is dominated by HEFA. This is largely due to HEFA projects having an acceptable technology risk to investors. This is because HEFA uses mature technologies that already exist in refining and adapting them to the production of SAF via HEFA, and HEFA projects are profitable. However, as you can see here, the HEFA demand, it builds and dominates the market between now and 2030. But from 2030 to 2035, the demand anticipated for SAF globally falls short by 23 million tons per year. And so this gap needs to be addressed by second-generation SAF pathways such as Fischer-Tropsch. As these projects take a long time to develop, so we're now at 2025, moving into 2026. These projects need to be starting to move through the feasibility stages now. We cannot wait until 2030 in order to meet this demand. So India has huge potential for SAF with abundance of available feedstock that can be converted to SAF. So you've got 750 million tons of biomass available, 230 million tons of surplus agricultural residue. Indigenous SAF has been explored already with the use in sugarcane, molasses, bagasse, and maize. The estimated SAF potential in India is in excess of 19 to 24 million tons per year. So as you can see, there's a huge opportunity here. I just want to highlight where Fischer-Tropsch fits into the production of SAF. So on this slide, you can see there's three main pathways. So at the top there, we have biogas to fuels. So in the biogas to fuels, you take a sustainably generated biogas, for example, landfill gas, which is cleaned up. That is then reformed into synthesis gas, so a combination of CO and H2. Which needs to then be conditioned to meet the spec of a roughly 2-to-1 ratio of hydrogen to CO for the Fischer-Tropsch synthesis path. The synthesis gas is then reformed into Fischer-Tropsch liquids, which are then upgraded to SAF by cracking and isomerization. Second to that, we have the solid waste pathway. In this pathway, you take solid waste, which is then gasified at high temperatures to produce syngas. This requires some cleanup to get it on spec, such as the removal of contaminants and adjustment of the hydrogen to CO ratio. This again leads into the same downstream processing through the FT synthesis and then product upgrading. And then finally, you have PTL. And PTL uses green electrons to produce hydrogen from the electrolysis of water. This is then combined with CO formed from the conversion of CO2 from biogenic sources into CO, which is then, again, generated into Fischer-Tropsch liquids through the Fischer-Tropsch synthesis process. I just want to touch a little bit on the comparable pathway of alcohol to jet and just highlight how that pathway is formed and what processes are involved. what you'll see on the right there is what everyone sees as the traditional A to J process, showing the dehydration, the agglomerization, hydrogenation, and fractionation from alcohols into SAF. But I just want to highlight that that is not the only pathway. The only process is required. You need to generate the ethanol originally. So as you can see on the left there, there's many different processes. So for example, gasification, catalytic conversion, reforming, and methanol synthesis, all required there to produce the alcohol required on the A to J route. So I just want to highlight that it's not just the A to J process. This process takes as many, if not more, processes than the FT pathway. Okay, I just wanted to highlight that FT is an already approved and certified fuel, unlike some other pathways which are still pending their certification. Now moving on to how Velocis can help. So Velocis is the combination of two companies. So it was formed from Oxford Catalysts, an Oxford University spin-out that had a superactive catalyst, and Velocis, a reactor supplier that had a reactor with high heat removal microchannel reactor. These two combined to form a reactor that was able to utilize the superactive catalyst with the high heat removal to form a compact chemistry and lower the costs. Velocis' micro FTL solution includes everything required for project developers: an FT license, a process design package, proprietary catalysts, automated controls, and FT island design services. You'll see here in the center of the picture, we've got what's at the center of the process is the Velocis microchannel reactor. This takes syngas, converts it into Fischer-Tropsch liquids, which is then separated to remove the tails gas such that it can be recirculated to improve the efficiency of the unit. There are three distinct differentiators for Velocis: a superactive catalyst, which delivers more yield for a smaller throughput and superior economics; proven FT technology, which delivers the highest TRL in the renewable fuel space; and standard reactors and modular design, which reduce project costs, risks, and delivery times. So superactive catalyst. So what does this mean? This means that Velocis reactors are many times more productive than comparable conventional fixed bed and slurry bed reactors. This enables greater yields for less catalysts, less space, and ultimately reduces footprint and capex costs while still delivering superior production. Velocis' high single pass conversion allows us to have industry-leading overall CO conversion across our unit of over 96%. What this means is that for the same syngas feed, we produce more FT liquids, thus reducing the need for expensive recycles to convert unconverted CO and methane into additional syngas. This enables us to convert more of the carbon monoxide into precious C5+ liquids, and this delivers a potential for increased revenue and greater MPV in the order of 10 to 50%. Micro FTL technology is piloted, proven, and commercial. We have over 300,000 hours of on-stream lab testing. This is equivalent of 34+ years of lab runs. Additionally to that, we've piloted our plant, integrated it under harsh conditions, receiving syngas from a gasifier, enabling us to test our reactors in harsh conditions and to prove its resilience to varying feeds. And finally, we were able to demonstrate our technology on commercial scale on the NVIA Energy Oklahoma plant, which was a landfill gas to fuels plant, which utilized two of Velocis' commercial reactors, producing 250 barrels per day of renewable fuel production and 6,000+ hours of cumulative operation across two commercial scale reactors. We were also involved in a demonstration in coordination with Toyo and Nido in Japan, in which our fuel generated from our unit formed part of the first commercial flight using SAF from wood chips in 2021 between Tokyo and Sapporo. The microchannel reactor scales up using a proven strategy. From the lab through to the pilot and the commercial, we use the same dimensions. What that means is that the results gained during our lab testing and through the demos are very representative for the commercial scale, and it scales up in a linear and predictable fashion, reducing risk. What you can see here is our commercial size reactor. It's formed by 4 cores of alternating process and cooling channels. In the process channel, we have our catalyst packed in there where syngas flows down and out the bottom flows FT liquids. This is cooled by microchannels where boiler feed water is fed through and partially vaporized to remove the heat. This intimate design allows us to reduce hotspots and improve the selectivity and control of our reactor and manage the superactive catalyst. Velocys offers a flexible solution. We have smaller single-core reactors suitable for 30 to 50 barrels per day of FT liquid production, and then we have a larger 4-core commercial reactor for capacities up to 200 barrels per day. This is then combined together in trains to scale up and to scale down to any of our customers' needs for their desired projects. Here we have our reactors being installed in the NVIDIA location. As you can see, they're very small, very compact, easy to transport and easy to install. This enables us to deliver our reactors in a distributed manner where the source of syngas is to provide FT liquids where it's needed. Velocys' FT licensing model is taking off. Recently, we've announced our license being selected as preferred FT licenser for the Syzygy project in Uruguay, which is converting dairy-derived biogas into SAF via Syzygy's proprietary reforming technology. Additional to that, we're partnering with NextChem and their advanced gasification process for the waste to fuels project in Imminent, Alto in the UK. We're also continuing our relationship with Nido and Toyo to continue the advancement of SAF projects in Japan, and we have a strategic partnership with Sekisui, an advanced CO2 to CO technology to produce highly efficient power to liquids. Post-HEFA, FT is your highest TRL commercially proven pathway to SAF, and Velocys is at the forefront of this. We've demonstrated our unit across the world with thousands of hours of commercial demonstration, piloted and lab testing. Velocys is ready today to help India meet its SAF demand through second generation, through technology licensing, FT reactor supply and catalyst supply. Thank you.